Alright, this is my connected objects number 2, and all I want to do is, we kind of already went over it, but the last type of problem I showed you was the one we worked where it was like this basic type, an Atwoods machine. Type of question. Sometimes some people call this a modified Atwoods machine. It's also a pretty common physics lab. It's where you have, let's say, a table like this, pulley on the end of the table, block up on top of the table, let's say another block hanging off the side, string connects like this. We might say that this is a 2 kilogram weight, and this could be a I don't know, we'll make this one a 4 kilogram. We'll use the same numbers as last time. So a 2 and a 4 massless pulley over here. Let's do this problem twice. Let's do it once without friction and once with friction. I'm not going to solve it out completely, but here we'll take a look at it. You would once again need 2 free body diagrams. So let's do it first without a coefficient of friction. So without a coefficient of friction, look at this first object up here. You'd have a tension to the right. You've got, and we'll call this M1, and we'll call this one over here M2. You've got an M1G going down, and you've got a, as always, if any two surfaces are in contact at 90 degrees to the surface, you've got a normal force going up. Now this second object has no x's whatsoever. All it's got is the tension in the positive y direction. So you've got your tension going up in this one, and then going down you've got an M2G. And it's very important in these connected objects, whenever you do your M1Gs, you do like M1G, you do M2G. And then when you write out your equals MAs, you write equals M1 or M2A. So this is a problem without friction in it. So we could come back and say in this one, sum of the forces X would be equal to. Now, in this one, you've got to come back and say, all right, the only X you have is tension, so there's minus nothing, equals, in this problem, it's moving to the right, so we say equals, well, in this case, positive, M1A. You don't have to put positive. I kind of messed up there. Equals positive M1A. Sum of the forces Y, there is no movement in the Y direction, no acceleration, so that's going to be equal to N minus M1G equals 0 for your Y components on this one. This one over here, you end up with, let's see if we can do this one. I'm not going to write sum of the forces X because there are none. Sum of the forces Y would be equal to T minus M2G equals, now the trick that I taught you in the last video, to make this problem work, notice how it's falling downwards in this one. So I'm going to write it's equal to negative M2A when I work this out. And that will make this problem work. And this method will work on any connected object. Now, all we would have to do is, this equation's already solved for T, so we would take this, plug it in here, and you would have M1A minus M2G equals negative M2A. Get your terms on the same sides. M1A plus M2A equals M2G. Solve for A. A times M1 plus M2 equals M2G. If you were looking for an answer, we'll go ahead and do it on this one. A would be M1 plus M2, so we've got 4 plus 2 equals 2 times 9.8. So this is going to be 19.6 divided by 6, 3.27. So there's our answer for A. If we want to find what tension is, we can come back here. Tension is equal to M1, 4 times 3.27, which is 13.1 newtons of tension in this problem. All right. Let's take a look at this same problem now and see what would happen if we put friction into this problem. So let's take a look. Same question, but with a tension in the problem. So we'll do the same thing again. Same exact setup. Boom. I like saying boom a lot. It's kind of relaxing. Boom. I'll do it again. It's my video. You don't have to watch. It gives me something to do. I'll draw. All right. We'll do the same. 4 kilograms, 2 kilograms. And this time we'll say that there's a mu of 0.2 up here for a friction between these two. And all that's going to do, let's write out our free body diagrams again. In the world of physics, these diagrams are of the utmost importance. Sounds kind of smart when I say it like utmost importance. Let's see. Let's go back to this object on the left. This will be my 4 kilogram. M1 is 4 kilograms. M2, I'm going to say it's 2 kilograms. So we'll go back, and I will say for this one we've got an M1G going down. We've got a normal force at 90 degrees to the surface directed up. You've got this rope attached to the right side, so you've got tension going this way. But in this problem you have a friction, which means in this direction we have a mu n working against that tension, opposing the motion. Now the other object is still going to be T up and M2G directed down on the other. So there's what our free bodies look like for both of these. So let's slide this up. Sum of the forces X would be equal to T minus mu n, since it's in the opposite direction, and that's going to be equal to M1A. Sum of the forces Y would be equal to N minus M1G equal to 0. This object, we have no sum of the forces Y for this, or sum of the forces X, excuse me, for this object. So we'll go straight into the sum of the forces Y, which would be T minus M2G equals, and once again, this object is falling down, so we would say it's equal to negative M2A at this point. All right. The physics is done. This problem's now just turned into a straight up algebra question. If we're looking again for tension and acceleration, we would now solve this for n. N would be equal to m1g. Plug it in up into this equation. So T minus mu m1g equals m1a. By the way, I want to say something here. On some of the forces X and Y, one of these two should always be equal to 0. If you catch yourself trying to write both of them equal to MA, you've messed this problem up. So you're not going to see that in these basic problems. Solve this equation for T. T would be equal to M1A plus mu M1G. Now take this, substitute it in over here. We're going to have M1A plus mu M1G minus M2G equals negative M2A on this side. So just like in all our other algebra problems, let's get our variables all on the same side. So we end up with M1A plus M2A equals M2G minus mu M1G on the other side. Factor out the A times M1 plus M2 equals, we could factor G out of this if we wanted, I'm not going to do it, minus mu M1G, and we could plug in our numbers now. A times what we have, 4 plus 2 equals 2 times 9.8 minus 0.2 times 4 times 9.8. And sorry, my writing's getting really bad right here. But anyway, let's see if we can plug all this in. So we've got 2 times 9.8, which is 19.6, minus 0.2 times 4. And, ooh, I put 0.5, so I'm glad I caught that. 0.2 times 4 times 9.8 divided by 6 is 1.96. Meters per second square. Once again, ask yourself, does this answer make sense? Yes, it does, because you can sit here and see that we're less than 9.8. If we want to find what the tension is, all we'd have to do is come back here. We'd have 4 times 1.96 plus 0.2 times 4 times 9.8. So 4 times 1.96 plus 0.2 times 4 times 9.8, and that equals 15.68. So we'll go 15.7 newtons. There is our tension. And you can see this one took just a little bit longer. The algebra looks just a little bit more in depth because of the extra thing. We did have to use this sum of the forces y. Let's do, I'm going to go on number 3. I'm going to do one more video in this series, maybe 2 more. I want to show you like 2 more harder examples if you need them. You might be able to go on right now, but I want to do one at an angle.